Hi, everyone, and welcome to the next CSC 232 lecture. This is going to be a bit of a longer one on vector and matrix operations. We're going to go into a bit of like the linear algebra, which hopefully you've all remember from linear algebra. I think you have to all take that for your majors. And then we're also going to go into how to make it work in Numpy. So first, we've got little reminder of our arrays as vectors. Right? We can think of our np.arrays as vectors. So this first one is just a vector 1, 0, -3. Then we can make it an explicitly like a row vector. You've got row vectors and column vectors. So this is an explicit row vector. See the double brackets. So this is saying now it's got one element in the first dimension and 3 in the second. So one row, one row with 3 columns in that row. So 2, -2, and 5. You can see the shape 1, and 3, and then you take the transpose of that flips it into a column vector, and it's 3, -1, because this is an explicit row vector. If you were to take the transpose of A, this is just a general vector, not specifically a row vector. Shape is 3, there's no second dimension. It's just a one-dimensional thing. The transpose doesn't add a second dimension. It stays as a one-dimensional thing. Now C is an explicit column vector. So this has 3 rows with 1 column per row. The shape is 3, 1. You can see what that looks like over here. And then you can also compose multiple vectors together, right? So now we're making a 3x3 matrix, which is row vector, row vector, row vector stacked on top of each other. That displays like this. And so this is all should be a bit of a review from what we've already been doing with arrays as vectors, or with arrays in Numpy. Reviewing some of the operations as well. We can multiply, right? This is element wise. So 2 star our array is just going to multiply 2 by every element. So first one becomes 2, second one becomes 4, third one becomes 6. We can divide, that's also element wise. Adding or subtracting, still element wise. All operations that are normal Python math operations are element wise. But when we multiply 2 vectors together, if you think back to your math classes, there's multiple ways to do that. There's the cross product and the dot product, and then also element wise. And so the dot product, v1 dot v2 is a1 times a2 plus b1 times b2 plus c1 times c2. And in Numpy, there's 2 ways to do that. It's with the dot function, so v1 dot v2, or this at operator. The at operator is matrix multiplication, which matrix multiplication is just the repeated dot product. So you can use the at operator on 2 vectors and you'll end up doing the dot product. See, these both give the same answer, 32. Then the cross product, remember back from math, the cross product is the thing with the right-hand rule, and it's giving you a vector orthogonal or perpendicular to your other 2 vectors. So if you've got your vector v1 and your vector v2, then your dot product is going to be this vector v3 that comes out at a 90-degree angle to v1 and v2. Math, a little bit more complicated, but this is the one where you would cover that first position and then multiply the second one. So to get the vector in the first position, you would multiply b1 times c2 and subtract c1 times b2 from that, etc. Thankfully, you don't have to do that anymore. We can just say np.cross of v1 and v2. That'll give us a new vector in the form of this array. That's the cross product of v1 and v2. Then there's matrices. So we can multiply a matrix by a scalar value, and this is going to be element-wise. Same as multiplying arrays, so they're very consistent. This is our 3x2 matrix. And when we multiply it by 2, every element just gets multiplied by 2. You can also divide element-wise and add or subtract element-wise. However, you can add or subtract matrices together as well. And this is still element wise, but 1, 2, 3, 4, 5, 6 plus 6, 5, 4, 3, 2, 1, the reverse of that is just going to element wise add. So 1 plus 6, 7, 2 plus 5, 7. And we get this whole matrix of all sevens, 2 by 3. 2 by 3, 2 rows of 3, 2 rows of 3 columns each. You can also subtract element wise. That works the same way. Every element gets subtracted from the corresponding element in the other matrix. And then matrix multiplication. I remember this being very hard for me to learn the first time, and I remember having to look it up very frequently. But if we're multiplying a 2 by 3 matrix by a 3 by 2 matrix, then the result is a 2 by 2. And so these must match. What happens in here is we take the first row vector and dot it with the column vector, and that gives us the first position. And then to get the second spot over here, we dot the first row vector with the second column vector, and then second row with first column, second row with second column to get all these different positions. And the dimensions of the matrices are important. So when you've got this m by n matrix and you're multiplying it by a p by q matrix, n and p must match. So this is a 2 by 3, and you can multiply it by a 3 by 2, and that's okay, but you couldn't multiply it by a 2 by 2. However, you could multiply it by a 3 by 5, and then your answer would be a 2 by 5 matrix. So m and q don't have to match. These two 2's match just by coincidence, but n and p have to match. And Numpy will throw an error if you try to multiply matrices that don't match, because matrix multiplication is not defined for those. Oh, and the result will be an m by q matrix. So dot product is defined for matrices. So you can use the dot product as matrix multiplication. And you can see here, we're multiplying a 1 by 3 matrix by a 3 by 1 matrix, which is really vector multiplication is a subset of matrix multiplication, where the matrices happen to be with 1 as one dimension. So this is a 1 row by 3 column. This is a 3 row by 1 column. You can think of these, it's just a 3 by 1 matrix and a 1 by 3 matrix. So we multiply these together, matrix multiplication style, we end up with a 1 by 1 matrix, which is just as we saw in the previous slide. Here, 1 by 1 gives us this position. So we just take the dot product of this 1, 2, 3, and this 4, 5, 6. And so that's why this at operator, which is matrix multiplication, that's why this does the same thing as the dot. And you can see our result here is this array. It's a 1 by 1, so it's got the double brackets wrapped around it to show that it has 2 dimensions. Now here we can also multiply a column vector by a row vector, and these are explicit vectors, whereas these were explicitly row vectors. And here we're going to be multiplying a 3 by 1 and a 1 by 3. So note that now the 1s are the part that matches. And so we're going to end up with a 3 by 3 matrix. We alternately, this second matrix, V2, could have more elements. It could be a 1 by 4 matrix, and then our final matrix would be a 3 by 4. It can be tricky to, or it can be easy to get confused with what's a row vector, what's a column vector. Generally, if you ever want to know what something is in your code, just call whatever your vector name is, in this case v1 dot shape, and that'll print out the shape, so you know exactly how many dimensions you have in each, or how many items you have in each dimension. Then there's raising a matrix to a power. So a cubed is the matrix multiplication of a times a, which would be the same as a at a at a. There's a helper function for that, np.linalg.matrix power. And so this is going to raise your matrix to whatever power, in this case, a to the third. if you were to do the exponentiation operator, the star star, so a star star 3, this is going to be element-wise or exponentiation. So it's going to be a times a element-wise times a element-wise again. And you can see these two different arrays are different, or these two different matrices. You get completely different results. One's element-wise and one's the proper matrix power. And then the identity matrix. So thinking back to math, the identity matrix is the square matrix whose diagonal elements are 1, and anything that's non-diagonal is 0. So down here is the 2 by 2 identity matrix. 1's the diagonals, 0 on the not diagonal. And properties of the identity matrix, if you multiply a by I, you get a. And if you multiply I by a, you still get a. This is the matrix multiplication. And a and I have to have the same dimension. Same as thinking back to regular math, x times 1 is equal to x, and 1 times x is also equal to x. So here's the 2 by 2. And so if we multiply this a by this identity matrix, we can convince yourself by going through this math, but you will get back the same exact matrix you put in. Dividing, so a inverse, a to the negative 1 power is the inverse of matrix A. A times A inverse is equal to the identity matrix, just like dividing x by x is equal to 1. Not all matrices have their inverse, so the inverse only exists if the determinant is 0, and in the case of a 2 by 2 matrix, this determinant is AD minus BC, and so if that is not 0, then you can take the inverse of it. So inverse and determinant, right, here we've got our A is A, B, C, D, and A inverse is 1 divided by the determinant times the matrix flipped in negative. And so here we have the actual A inverse. And then if we multiply A by A inverse, we get back 1, 0, 0, 1. Even though this looks like something chaotic and crazy, and you can't imagine that multiplying this by that will give back such a concise, clean product, because this is the inverse of A, and by the property that A times A inverse is equal to the identity matrix, we get this back. Now, to do this all in Numpy is a lot simpler than to do it by hand. So if we create our matrix A, 4, 1, 2, 3, and then to get the inverse of A, we use the NumPy function np.linalg.inverse, or inv of A, and that gives us this array right back. And then to get the determinant, we use .det. That gives us our determinant. And so here, to get the identity matrix, fancy way of getting it, we're going to take our matrix A and we're going to multiply it using the dot operator. Could also use that at sign operator here, but A multiplied by the inverse of A, np.linalg.inv, and then that is going to be equal to the identity matrix 2. To get the identity matrix in NumPy, it's np.eye as in I, pretty punny there. So I of 2 is the identity matrix of a 2 by 2. Some other matrix properties. We don't need to go through all these in detail, but pretty much if you can do it to a matrix, you can do it to a matrix using NumPy. You can get the norms, the trace of the matrix, and then the rank, and anything else you can do to a matrix with linear algebra. This includes solving linear equations, which is super powerful and will definitely come in handy in your later engineering classes. Big plug for this class. So if we've got this system of linear equations, x minus 2y equals 1 and 3x plus 2y equals 11, then that can be represented as this matrix times this column vector. So 1 minus 2, the coefficients here, times x, because we want that first result to be this dot this. And then 3x plus 2y, so we get our 3 and our 2, and then our y over here. And that's equal to these results, 1 and 11. And then solving this system, we can just divide by the answer we're expecting, move it over, and then eventually get 3, 1. And we can also do that really quickly in Numpy by creating our M, our input array. That's based off the coefficients of these systems of linear equations. And then B, the answers we're looking for. And we can solve that by just saying np.linalgebra.solve with our M and our B. And that will give us our solution as a matrix, or in this case, a specialized version of a matrix, which is this vector. However, if there's no unique solution, then a linear algebra error is raised. So watch out for those. And definitely write this stuff out on paper before you try to put it into code, because this is pretty clear what's going on. And this down here is, at first sight, I would say not clear at all. So make sure you know exactly what you're trying to do and then translate it into code. Finally, element-wise multiplication, use the normal multiplying operator instead of the @ sign. So you can multiply two matrices together, and we saw this a little bit earlier when we were looking at the exponentiation operator. But if we want to multiply A times B with like element-wise, so multiply 1 by 5, 2 by 6, 3 by 7, 4 by 8, then we just do A asterisk B, and that gives us this. The shapes, however, must match exactly when you're doing element-wise, because we need a mapping from this first element to this element. And if this were, for example, a 2 by 3, then we wouldn't know what to do with those bottom two elements. However, Numpy does do this thing called broadcasting, where it will repeat elements of your array or your vector to make it satisfy the shape that's required. So we've seen this a bit earlier when you multiply, for example, your vector of any one-dimensional vector or one-dimensional array by a constant number. So if you're multiplying your vector, say 5, 4, 3, 2, 1 by the number 2, you just want to double everything. What Numpy does behind the scenes is makes you a vector of the same shape of just 2's and then multiplies that element-wise. So in the case of a matrix, if you've got your array, or you've got your matrix A, which is a 2 by 2 matrix, and then you've got your one generic vector, which is just a 2 comma blank or 2 comma 1. Then what Numpy is going to do when you multiply these together is it's going to broadcast B into a 2 by 2 matrix. So it's just going to copy that row vector and then put it below to make it now a 2 by 2. So we get 2, 3, 2, 3. And then it will multiply these together. So 1 times 2, 2, 2 times 3, 6, 3 times 2, 6, and 4 times 3, 12. Broadcasting can be really helpful, and you just have to be aware that it's happening. So it's helpful in the sense that we don't have to manually create like a, say we want to multiply a 32 row matrix by 5, right? Then we wouldn't have to create a 32 row matrix with the number 5 at every spot. We can just multiply that by the scalar value 5. Generally, broadcasting only works when the dimension of like at least one dimension is 1, because then it can just copy everything from those other dimensions over in that dimension. But if this were a 3 by 2, for example, it wouldn't be able to broadcast these together. And then element-wise division, you can just use the divide symbol. So A divided by B is going to do the element-wise division of A divided by B. 2 gets divided by 2, 3 by 3, 6 by 3, and 8 by 2. End up with this final array. The shapes must match, but again, broadcasting may be possible in the case where one of the shapes has 1 as one dimension. Finally, in summary, there's all these vector operations that we can do. Important new ones are the dot product and the cross product, ways to multiply vectors together. Those are a subset of the matrix operations. They're a special case. but can really be thought of as just matrix operations. So we can do the dot product, which is multiply with the at sign. We can do matrix division, which is dot product between a matrix and the inverse of that matrix. And then there's the element-wise operators, multiply, divide, plus, and minus. And in this case, the shapes must match perfectly. But sometimes you can broadcast. And then finally, solving linear equations is very powerful and a good reason to take this class. All right, and that's everything for this lecture. I look forward to seeing you all next week on Monday.